let's look at a problem in the book on relative motion. I enjoy sailing, and this is something that comes up all the time when you're sailing. We have an apparent wind angle. We have the true wind, and we have the boat speed. So imagine the following before we do that problem. Imagine we're in our boat, and let's say it's a power boat. And we're heading, let's say we can move the power boat at 10 miles an hour. And we're heading straight into a breeze. Straight into a breeze, say a 5 mile an hour breeze. What's the apparent wind?
18 miles per hour.
We're heading into the wind at 10 miles an hour, and the wind's blowing towards us at 5 miles an hour, right? So the apparent wind is 15 miles an hour. Okay, you turn the boat around real quick. Now you're going downwind at 10 miles an hour in the water with a tailwind of 5 miles an hour. You feel what?
5 miles an hour.
5 miles an hour. You slow your motorboat down to 5 miles an hour. It's still heading downwind.
It's dead calm.
Feels like it's dead calm. And if it's 90 degrees out that day, you'd probably want to either be going into the wind or speed up in your boat. Okay, so you got some kind of a breeze effect. Does that make sense? Mm-hmm. I notice it all the time when I'm out sailing. Okay. Except I can't go straight into the wind on a sailboat. Okay. So what we want to do is we want to tackle a problem like this in a similar way to what we just tried with that sample problem. What information do they provide us?
Wind speed.
What's the wind speed?
Hull speed. Hull speed.
Oh, the hull speed is the
6.5 knots.
6.5 knots?
Yep.
Okay. What does, this is the boat speed, right?
Yeah.
Okay, so this is the speed of the boat. We'll call that V sub B. Knots.
Nautical mile per second.
That means nautical mile per hour.
6,000 and some feet.
Nautical mile per hour. Nautical mile per hour. I believe a nautical mile is 1 minute of latitude. 1 minute of latitude.
Unless that's ridiculous, then it's 1 second.
Okay. So a minute of latitude in angle measure, a 60th of a degree of latitude. Okay. So that's larger than a statute mile. Statute mile that we're familiar with is 5,280 feet. A nautical mile is a touch over 6,000 feet. And it should be tabulated in an index or a table somewhere in the back of our book or inside front cover. Does it indicate anything? That's all right. We'll just stick with the given information here, so we don't need to convert our units. But most of our engineering books will have that kind of conversion in it. Okay. What else did they tell us in this problem?
Direction of the wind.
The direction
from the center line of the boat.
Okay. So we have the boat. So the boat is heading this direction. So there's the boat. And so the center line of the boat is heading that direction, and the wind is coming at us.
It's coming from 50, but the string says it's from 35.
Okay. Okay, we have a north wind, so the wind is coming directly from the north. So the velocity of the wind is coming this way. The angle is 50 degrees. But they also tell us, and notice they don't give us, let's see, they do give us the boat speed, don't they?
Yeah.
The velocity of the boat was 6.5 knots. They don't tell us the wind speed, but they do tell us its direction. It's a north wind coming out of the north. And they tell us the boat's direction, don't they?
You
Or
can
not.
derive it easily enough. since the
Well,
wind is coming
they
out of
show
the
us
north.
the apparent wind. They tell us that the apparent wind is coming at 35 degrees
From the center line.
from the center line of the boat, as shown. Okay. So the apparent wind is coming in this way at 35 degrees. Now, what kind of subscripting do we want to use on this thing right here? On this apparent wind speed. Is it the wind relative to the boat or the boat relative to the wind?
The
Wind relative to the boat.
It's the wind relative to the boat, like I was describing earlier on our motorboat. You're on the boat as the observer, usually. Unless you're the bird, maybe, that's gliding along with the wind, okay? So you're usually on the boat. Okay, so we have these pieces of information. Now, what's the question?
What's the true wind velocity?
Okay, what's the true wind velocity? What's the true wind velocity? So, how do we write the equation? How do we write the equation involving these three vectors? Okay, if you aren't sure, just write it and then take a look at it and see if it looks right, see if it makes any sense. So VW equals the velocity of the boat, velocity of the wind equals velocity of boat plus the velocity of the wind relative to the boat. You can look at your subscripting here to check to see if it's in the right form. Okay. All right? And that should be consistent with what you observed over here when we derived these equations earlier on the other board here. Okay. So let's write in what we know. We don't know this thing's value, its magnitude, but we do know its direction. If we, let's lay in here, we need to lay an x and y axis system in here. So what direction should we set our axes?
Let's have X go along the line of the boat's travel.
Okay, so let's do that. So we define x this way, and we'll define y as perpendicular to that, and we'll write our vector equation based on those axes. So the wind's coming straight out of the north, so better be careful here. Tilt your head a little bit so you can see this, right? So notice the direction of the wind. If I reorient this, some people need that. We've got the wind coming in like this at 50 degrees, don't we? To our x-axis. So we have a left component, don't we? Which is a cosine component of 50 degrees. Negative. Negative VW. And actually what I'm going to do is I'm going to make a unit vector because I don't know the wind velocity. So my unit vector is going to be negative cosine 50 degrees, comma. Well, let me go ahead and use ij. I hat. And then the y component is downward, so that's going to be a negative sine 50. J hat. Everybody comfortable? Look at it here in the original. You can see this velocity of the wind has a negative x component and a negative y component. Negative x, negative y. The velocity of the boat, I like that one, 6.5 I. And the apparent wind that we can sense when we're on the boat, we can sense that on the boat, is unknown magnitude, right? Unknown magnitude, but in this direction of 35 degrees. So if I draw it separately, here's the velocity of the wind relative to the boat. That's at 35 degrees relative to our x-axis. And again, negative and negative on the components. Unknown magnitude again. And I'll use the vector notation just to be able to fit it in here. Minus cosine 35 degrees minus sine 35 degrees. Now we look at this vector equation, and do we get nervous?
No.
We've got two unknowns.
Yeah, but we got two equations because it's vectors. You can break it apart.
Oh, we've got two equations actually here, don't we? We have two scalar equations, okay? So we have a vector equation here, but it decomposes into a pair of scalar equations. So our x-directed components off of this, negative VW cosine 50 degrees must be equal to 6.5 minus the velocity of the wind relative to the boat, cosine 35 degrees. And the y-directed components, negative velocity of the wind sine of 50 degrees is equal to the y component over there, negative the velocity of the wind relative to the boat, sine of 35 degrees. Now we feel better. We have two equations with two unknowns. If we wanted to go directly towards our answer, we would want to eliminate the velocity of the wind relative to the boat, right? To seek our answer most efficiently. Seek our answer most efficiently. Right? Mm-hmm. So if I want to eliminate this variable, then I'm going to solve for it, and this equation would be easiest, and then tuck this result for that back into the first equation. So from equation 2, this is equation 1 and equation 2, from equation 2, the velocity of the wind relative to the boat is equal to the velocity of the wind sine of 50 degrees divided by the sine of 35 degrees. And if somebody would go ahead, I'm going to leave those as is for a second as an intermediate result. And let's come over here now, and we're now going to substitute 2 into equation 1. And so we have minus the velocity of the wind cosine of 50 degrees is equal to 6.5 minus our substituted expression, the velocity of the wind sine of 50 degrees divided by sine of 35 degrees times the cosine of 35 degrees. Feel good? If we move the terms involving the wind speed over to the left side here and factor out that wind speed, we'd be left with minus cosine 50 degrees plus sine of 50 degrees, and here's a sine cosine ratio which we could put down in the denominator as the tangent of 35 degrees to allow easy use of our calculator, and that's equal to the 6.5. Finishing that off, the velocity of the wind then, magnitude, is the 6.5 divided by this expression in the brackets. Make sure you're in degree mode. Somebody punch that up. 14.4 knots, nautical miles per hour. Okay. And while we're at it, let's go ahead and grab the other one. The velocity of the wind relative to the boat is equal to this 14.4 reading, approximately, times the sine of 50 over the sine of 35. And what'd you get?
19.24.
Anybody confirm that? Does that feel right to you? Do these values feel right? Imagine that, let's see, I'm on the boat. I'm heading that direction at my 6.5 knots. The wind, I know, is coming, the apparent wind is coming at me from 35 degrees here. Okay, they told us the true wind, if I stop my boat momentarily, I could sense the true wind is coming from 50 degrees off of my line of action. So it's coming at me from over here. Does it feel right to you that the relative speed of the wind to you should be greater than that wind speed?
Yeah,
Because there's a part, good, I think what you were saying was there's a part of the wind speed that your boat is contributing to adding to a portion of the wind speed. So it should sense you're heading somewhat into the wind on a tack, on a sailboat. Okay, so that should feel good. What if all of a sudden you forgot your vector algebra? Couldn't figure this problem out that way.
We got the trig and
Yeah, you have 3 angles on the side.
We've got 3 angles. We've got some angles known, don't we? That we could build this triangle, this vector triangle. We could build it with one side known, right? Let's see if we can sketch that. Let's see. If I've got my wind, here's my wind, unknown. And the way I usually would suggest you do this is just there's a line of action. There's a line of action known for the wind. Okay, a line of action known. And our equation we were playing with, I guess we do have to know a little bit about our equation. We have to know this much. So we need to know that. So this side of the equation, we know that direction. We know that the boat's direction is what?
at some direction off
50
that.
degrees away from that, correct?
50 degrees away from that. And it's
Clockwise.
okay over here.
Okay.
And we know that is 6.5, right? We know that's 6.5. Good. Now, added, this is the velocity of the boat here. Added on to that is the relative velocity, wind relative to the boat. And what direction is that? I have to add it onto the tip of this. I have to go out here on the tip.
Down.
Which way?
Down towards you.
35 degrees, right? Where that's 35 degrees. Right?
The wind on this side.
And the wind's coming from there. So how does this connect? This side of our equation has to be this vector leg. It's not up here though, is it? It's got to be down here. Okay? And this angle right in there was 50 degrees. So therefore, this angle's 50 degrees, which means this is 130 degrees, which means that this angle has to be the supplement to the sum of those, 165, 75, 15 degrees. Pretty good sketch, huh? Okay. Not bad, huh? So we're looking for this thing over here, and this is the relative thing, wind relative to the boat. And somebody said law of sines. Now look at the given information. We know side, angle, angle if we work our way around the triangle. So
You could just do a trig.
why don't we just use law of sines is actually the easiest way to do it. So let's take the given pair. Let's say we're shooting for this guy. So the velocity of the wind is to its opposite side, sine of 35 degrees, as the velocity of the boat is to the sine of its opposite angle, sine of 15 degrees. So we forgot our vector algebra. We just decided to be artistic about it with a relative scale drawing. And we end up punching this up. And look at this math right here. Where was it? Oh, that's looking a little more. I think this actually would tidy up some. What'd you get?
14.4.
Oh, good. I'm glad. Okay. So you're able to get it from a graphical perspective. Try to do these at this section of the book. Try to do them both ways. Use vector algebra and then also try to do a sketch like this. The reason is later on in the course, vector algebra and sketches are absolutely critical for more complex mechanisms later in the course, and more advanced dynamics as well. Okay. What we're going to do on tomorrow or next class session is I answer some additional questions that you might have on the more recent material then, and then we're going to go ahead and start talking about constrained motion, where we might hook a couple of items together. And you've probably seen this in physics. An item hooked on a ramp with friction, a block, and then maybe it goes up through some pulley mechanism over the top, and then there's some other hanging weight there, and those things are going to be moving relative to one another. They're moving relative to one another. And so that's called constrained motion. And you can look at the book in the next section there and sort of get a glimpse of those kind of problems. So we'll get started on that in the next class session. Questions?
Are you going to collect any homework on Thursday?
No. Okay. No homework on Thursday. I'll try to get your homework number 3 back to you by then. And we'll probably have a quiz next week. Quiz. And I haven't decided what. It'll either be an in-class quiz. It might be where I have you out of class, come over to the resource center and take it over there, or I might give you a take-home quiz. I haven't figured that out yet. Okay, so try to keep up with me. That's it.
Have you an idea as to the extent of the next homework assignment?
Just a second. Let's wait till they queue out.